2. Inorganic compounds are structurally simple and they usually lack carbon. Here's an example: sodium or potassium chloride, the salt. Organic compounds, more complex, always contain carbon. Here's an example: cholesterol. You can see here's a carbon ring connected to another carbon ring, called a carbon ring because the corners have carbons in them. And here's a carbon chain. And they usually contain hydrogen, 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 lots of hydrogen, and they always have covalent bonds. Here's an example of a covalent bond. Remember, covalent bonds are the strong bonds. Water is inorganic. It's the most important and abundant in living things, and it's most unique due to its polarity. We talked about before how there's unequal sharing of electrons, which makes oxygen a little slightly negative and hydrogen slightly positive. And it's allowed, because of this, it's allowed to collide with reactants to produce more reactions. Here we see water right here and salt, table salt, NaCl. And water comes in and breaks up NaCl into its ions, sodium and chloride. Water is in a solution is the solvent. It does the dissolving, and whatever is being dissolved is the solute. So in that last example, salt would be the solute. Substances that contain mostly polar covalent bonds are known as hydrophilic, meaning they dissolve well in water, they like water. They mix with water well. Substances that have mostly non-polar covalent bonds are hydrophobic. They do not combine well with water. They're afraid of water. They have a phobia of water. Because of water being polar in its bent shape, it allows it to interact with many ions or molecules. And because of its role as a solvent in the body, doing a lot of dissolving, it's very important and crucial to health and survival. The pH scale. It's a scale that runs from 0 to 14, 7 being neutral, less than 7 being acidic, more than 7 being base or alkaline. And you can see on the scale that closer you get to 0, the more acidic is. So a pH of 1 is less acidic than a pH of 0, and bases a pH of 14 is more of a base than a pH of 13. When you see pH equals negative log H plus is the concentration of hydrogen ions that you find in that solution. The red also represents hydrogen ions, and the blue represents hydroxide. So we can see here pHs that are less than 7 have more hydrogen ions than hydroxides, and bases have more hydroxide ions, hydrogen. It's a logarithmic scale, meaning every number is a tenfold difference in the amount of hydrogen ion concentrations, not just one. So here's an example. A pH of 1 is 100 times more concentrated with hydrogen ions than a solution that has a pH of 3. 100 times more. If it was a pH of 2 being compared here, it would only be 10 times more. So you move the decimal place over. A solution with a pH of 11 contains 1,000 times less hydrogen ions than a pH with 8. Let that sink in. pH less than 7 is acidic, meaning it has more hydrogen ions than hydroxide. pH greater than 7 is alkaline or basic, less hydroxide ions. And salt has a pH, it's neutral. So homeostasis, your body has to maintain appropriate pH levels in all your body fluids. Blood, for example, is a pH of 7.35 to 7.45. If it's not maintained, if you're too acidic or too basic, that can lead to death quite quickly, actually. Your body has these buffer systems. They buffer the pH. And the buffer system itself is made up of usually a weak acid and a weak base. And what it will do is, let's say you've taken a strong acid like Mountain Dew, your body will then convert that strong acid to a weak acid by hiding excess hydrogen ions. Or they can take excess hydroxide ions. So if you take in bleach, which has a high pH, meaning it's a base, It will hide those excess hydrogen ions to protect your body. The major buffer system is called the carbonic acid bicarbonate buffer system. Functional groups, so organic molecules are made up of carbon, right? So you either have these carbon chains, okay, like this. There's a chain of carbons. You could also have the rings of carbons. That's not very good pentagon, but that's a ring of carbons. But off of those chains or rings of carbons, you have these things that are called functional groups. They are found attached to the carbon skeleton, and they give certain properties to that organic molecule. And some of the common ones we'll talk about: esters, amino, carboxyl, phosphate groups. Hydroxyl group, when you see an OH off the side here, so COH is called a hydroxyl group. It represents an alcohol. It's polar and hydrophilic. And that means it helps it dissolve easily in water. Carboxyl groups, we see a carbon double bonded to an oxygen and also bonded to a hydroxide is called a carboxyl, or seen like this. That's the way it's drawn out, but it's also written like this. We're going to see this on amino acids. Also, I want to point out aminos. Well, phosphate groups just has a P in it, which indicates it being phosphate. Esters kind of look like the carbonyl group, but they have what's called an R group attached to it, and that can change. Amino groups have a nitrogen, like that large there, a nitrogen. That's an amino group. They can act as a base and pick up hydrogen ion. And they are an amino or amino acids. All amino acids have one. Organic compounds, if you were to build organic compounds, a lot of them are polymers, which means simple units like Legos. If you were to stack the 2x2s up to the top, each Lego represents a monomer subunit, and if you attach them all, you're going to build a polymer. Organic compounds, large polymers, are also called macromolecules. So here's a starch, here's a monomer attached to another monomer, attached to another monomer. So a polymer is just a name for a large macromolecule. Isomers, these are kind of cool. They have the same molecular formula, so that means when you write it out, they have 6 carbons, 12 hydrogens, and 6 oxygens, C6H12O6, but their structural formula is different. That actually makes them different compounds. So here we have 2 different types of sugars, glucose and galactose. They both are C6H12O6, but you can see here, look on the ends. In this case, the hydrogen is up. Over here, the hydroxide group is up, and opposite on the other side. Carbohydrates provide most of the energy needed for life. It's all done here. So we'll stop there for part 1.